So, in the last lecture, if you recall, we were talking about some of the features of the Verilog language. In particular, we are discussing the net type variable. So, what are the different types of net type variables? Now, we continue our discussion here in this lecture. So, here we shall be first talking about the other data type that we talked about, in addition to net, the register data type. Now, register data type, by its very semantic, it means that it is a variable which can hold a value. Like, suppose I have defined a register x, then I can write a statement like x equal to a something, let us say x equal to a plus b. So, I can write something will get assigned to x. Okay. Now, this assignment will not be done using an assign statement, not continuous assignment, because I told in the last lecture that in an assign statement the left hand side must be a net type variable, it cannot be a register type variable. Okay. So, whenever you use a register type variable, there you are actually storing a value, it is supposed to hold the value till you are using it again. Okay. So, a register is a variable that can hold a value, and this is different from a net which is continuously driven and cannot hold any value, because if the line that is driving the net changes, the net variable immediately changes, it cannot hold it. But I also mentioned that this does not mean that a register variable will always map to a hardware register. This may or may not be true. There will be some cases which we shall be illustrating with examples, where you may be using a register variable in a Verilog code, but ultimately your circuit that will be synthesized will be a combinational circuit, right. So, the following register data types are supported in Verilog. The most widely used is something called reg, this is short form for register. Then you have integer, real and time. Integer is typically used for application where you want to count something, like number of times you are looping and so on, and real, as the name implies, this is used to store some floating point number with fractional parts, and time is a special variable which is used to keep track of simulation time. Now, you see, let me just emphasize one thing here, that we shall be talking about many features of Verilog which are simulation only features, that makes sense only when you are doing simulation. When you are carrying out synthesis, those features does not mean anything, and the synthesis tool will be simply ignoring them. Let me take some examples. See, whenever we instantiate a gate, we had seen some examples where you have specified some delays of these gates, right. Like we can using that hash symbol, I can write hash 5, hash 2, hash 1, but the synthesis tool will be ignoring that, those will be only for simulation purposes, because during synthesis, whenever an AND gate is actually implemented, so whatever is the actual delay of the AND gate, that will be the delay, right, not 1 or 2 or 3 whatever you are saying. Okay. Similarly, this time is something that relates to the time of simulation, this is never used during synthesis. Such variables will be ignored during synthesis. Okay. Let us start with reg. The first thing is that in the reg data type, so just after you declare, but you have not initialized it to any value, so the default value will start with undefined or x. A reg value can be assigned in several different ways, we shall be seeing that. They can be assigned in synchronism with a clock, or even without a clock you can do it. Now, there are two kinds of assignments we shall be learning, like for example, a reg type variable a you can either write an assignment like this, or you can write an assignment like this, less than equal to. So, their meanings are different, we shall be explaining these things later. Okay. But the point to note is that here A is a reg type variable. So, for these kind of assignments, the left hand side must be a reg type variable, right. Okay. So, some of the example declarations are shown here. Reg xy, well, if you simply specify the name of some variable like here x and y, they will be by default taken to be 1 bit variables, single bit variables. So, x is a 1 bit variable, y is a 1 bit variable. Well, you can also define a vector, we shall be talking about vector separately again. This is one example, reg within square bracket 15:0 bus. This means I am declaring a variable bus where there are 16 bits, 0 is the least significant bit, 15 is the most significant bit. So, I can define a 16 bit bus variable called bus using a statement like this. Now, a reg type variable, when it is used in an arithmetic expression, it is treated as an unsigned number without any sign. And another point is that when you are actually implementing some hardware register based design like counter, shift register, etc., then you must use reg, there is no other alternative. So, here there is one example which uses reg. Of course, here there are many constructs which I have not discussed yet, but this example you can appreciate what it is. Here we are trying to implement a counter. Counter, there are 3 ports, clock, reset and count. Clock and reset are the input and count is the output. As you can see, count is a 32 bit vector, 3120, that means this is a 32 bit counter. Well, ignore this reg for the time being, and this is the main body of the counter description. There is a statement called always, always at positive edge of the clock. So, in English it means this, always whenever there is a positive edge of the clock coming, you do this. What you do? You check if the reset signal is 1 on high or not. If it is high, you initialize count value, 32B0 means it is a 32 bit number, value is 0. So, you are initializing it to 0. If reset is 1, count is 0, else count equal to count plus 1. You do this every time clock edge, positive edge is coming. Now, as I said, such expression with equal to, so these are examples where you are using that. Well, you can have only a reg type value in the left hand side. That is why I have to separately declare the same variable count which was in the output also as a reg, because if you do not do this, your compiler will give you an error that left hand side variable type is wrong, right. So, here the count value is increasing at the positive edge of the clock, and if reset is high, the counter will be reset whenever the next clock comes, okay. It will be reset to 0. Now, there is another way of specifying this. You look at this previous one, here this always block was executing begin end whenever the positive edge of clock was coming. So, you think of a scenario like this. So, I have a clock, clock is coming like this. Okay. This is one positive edge, this is another positive edge, this is another positive edge means 0 to 1, 0 to 1 positive edge. So, this always block will get executed here, here and here, but suppose my reset signal I have made it high here, let us say I have made it high here and I have kept it high for some time, and then I have made it low. See here, even though I made the reset signal high here, but according to our previous design, the counter will be reset only here whenever the next positive edge of the clock comes. So, counter will be reset here, because the always block will be executing only when pos edge is coming. So, even if your reset has been activated here, it will be waiting for some time before the counter is actually reset. But there can be application where you may want that whenever reset is going high, you reset the counter immediately, right. So, our next design, which is a slight modification of this one, what we do? We change this always statement, we add another clause. What I say? We say always at positive edge of the clock or positive edge of reset. So, if the reset signal goes from 0 to 1, that will also cause the begin end to execute, and it will see that reset has become 1, it will immediately reset it to 0. So, this is an example of asynchronous reset, which means resetting is not happening in synchronism with the clock. Okay. So, you can have both these descriptions in Verilog as you want. Next comes the integer data type. Now, integer is a more general purpose type, actually where you can use it to store any arbitrarily integer values, mainly for counting some situations like loop counting. So, reg may not be very convenient there, because whenever you are counting something, the count value may sometime become negative. But as I said, in reg, a variable declared of type reg is always considered to be an unsigned quantity, it cannot have a negative value. Okay? Fine. So, integer data type, another feature is that it cannot have a size defined to it. So, the default size is 32 bits. But the point to note is that, well, if you are doing synthesis, again not for simulation, if you are doing synthesis, the synthesis tool will try to apply some intelligence. It will do some kind of data flow analysis and try to guess that what should be the value of the integer. Should I keep whole 32 bits or less than 32 bits should also be okay. Like you take an example. Suppose I have declared two wires x and y vectors of size 16 each, 0 to 15, okay, 16 bits, and I declared an integer of size c. So, as I said that whenever you declare an integer, you cannot specify any size. Then we write, sorry, this is not z, this is c, let me correct this, this is c. So, here if I write c equal to x plus y, this is also c. Yeah. So, if I write c equal to x plus y, what will happen? Two 16-bit numbers are added. So, the synthesis tool will see that x and y are 16-bit numbers, you are adding it. So, the sum can be maximum 17 bits, 16 bits plus a carry. So, when it realizes the hardware for C, it will not be implementing it as a 32-bit counter, rather it will be using it only as a 17-bit register. 17-bit is sufficient in this particular case. Okay. This is what I mean is that the synthesis tool will try to determine the size by carrying out some data flow analysis wherever possible. Okay. Talking about real data types, as the name implies, they are used to store floating point numbers, numbers with fractional parts. And just like in a high level language, so whenever you assign a real value to an integer, there is a little difference. Normally in a high level language like C, the number is truncated and the integer part is stored, but here it is rounded off. So, a small example, suppose I define two variables e and pi as real, and in the initial block which you have used seen in the test benches. This initial is normally used in the test benches. So, in an initial block, let us say I have initialized E to 2.718 and pi to, this is just a notation episode. I could have written 3.14159, but I have written 314.159 into 10 to the power minus 2. E minus 2 means 10 to the power minus 2, right. Now, suppose I declare an integer x and somewhere again inside an initial block I write x equal to pi. So, pi was 3.14. So, it will be rounded up and only the value 3 will be assigned to x, right. This is what I mean here. Okay. Now, time. Time is a data type which is used to keep track of simulation time. So, when simulation is carried out, well, you can use that Verilog that I had mentioned. You means you can use Verilog or any other tool which are available to simulate a Verilog design. So, when you do simulation, there is a notion of simulation time. You specify time, you specify gate delays, lot of things you do. So, just a small example, in the Verilog code you can define a variable, let us say current time is a variable of type time, and this special system function $time is there. So, anything starting with dollar is a system function. This system function actually gives you the current simulation time. So, in the initial block somewhere, if you want to assign the current time to this variable, you can write a statement like this, current time equal to $time. So, you can use the time data type in some application where you actually want to find out that to execute a block how much time it has taken, it took. So, you can print the time before, you can print the time after and see the difference, okay, like that. Fine. Now, let us come to vectors. We have seen single bit variables. Now, let us see how we can group such single bit variables to create something called vectors. So, nets or rich type variables, both of them, they can be declared as vectors. Vectors are nothing but multiple bit quantities, and if you do not specify this bit width, then by default it is taken to be 1 bit. So, some examples we have already seen. Vectors can be declared by specifying a range within square bracket, range 1 colon range 2. The convention is that the first one, range 1, is always the most significant bit of the number, and the rightmost one, range 2, is the least significant bit. Well, I will explain what it means. Let us see some examples. Suppose I write simply wire x y z. X y z are simple variables without any vector notation. These are single bit variables. So, if I write wire 7 colon 0 sum, what does this mean? This will mean that I have an 8 bit variable called sum. This is my sum. There are 8 bits. The index is 7 is the most significant, 0 is the least significant. The individual bits I can access by writing sum 0, sum 1 up to sum 7. Okay. This is just like an array, this is just like an array of bits. Okay. Similarly, another example MDR, this of course I have defined of type range. Well, now the point is that range 1, range 2 can be any arbitrary values. So, it is not necessary that range 1 must be greater than range 2. Like in this example, I have shown range 1 colon 10 data. So, how many numbers are there? 1 to 10, there are 10 numbers. So, actually here also we are declaring a register of size 10, but how? This is data, let us see. So, the name of the variable is data, and the way we have declared, range 1 was 1, range 2 was 10. So, the index values are defined like this 1, 2, 3, 4 up to 10. So, in this case, so if you use this data in an arithmetic expression, this particular bit will be treated as the most significant bit, this particular bit will be treated as the least significant bit. So, by specifying your range 1 and range 2 in a suitable way, you can choose to swap LSB MSB, like here in this case the 7 was the MSB and 0 was the LSB, but if you write 1 to 10, 1 becomes MSB, 10 becomes LSB. So, this convention has to be kept in mind. The first value of the range will be the bit on the left, the second value on the range will be the index bit index of the on the right. So, that will be your word. So, whenever you are using it, you should keep that in mind. Okay? All right. So, after we have seen this vector, let us see how we can use sections of a vector in an expression. So, what do we mean by sections of a vector? Suppose I have declared a vector of size something, let us say 32. So, the example I have shown is a vector of size 32, and I want to extract 5 bits from the middle of the vector and assign it to some variable. Now, that can I do it? Yes, I can do it. So, I can take out any cross section of a vector by specifying the starting and the ending index, and I can assign it to some variable. I can use it in an arithmetic expression, whatever I can do I want. Okay. Let me take an example. So, here I am taking an example of an instruction encoding. So, the example I have taken is a 32-bit instruction register that contains a 6-bit opcode, 3 register operands, 5 bits each, and an 11-bit offset. So, what I mean is something like this. Suppose I have a 32-bit instruction register. So, bits let us say from 0 to 31. So, what are the different fields? So, I have the first 6 fields are the opcode. First 6 fields means bit number 31 to bit number 26. Then I have 3 register operands. So, I call them reg 1, reg 2, reg 3. These are all 5-bit fields. So, the bit number will be 21 to 25, 16 to 20 and 11 to 15, and the last field is a field which is called offset. Offset is an 11-bit field 0 to 10. Suppose my instruction register has this format, there are 5 fields, right. So, what I can do is something like this. So, I can declare this register IR 32-bit, and I can declare the individual fields also. Opcode is a 6-bit field, reg 1, reg 2, reg 3 are 5-bit fields 4 to 0, offset is an 11-bit field. Then I can simply write opcode equal to IR 31:26. So, you see here, so we mentioned 31 to 26, opcode will be assigned 31:26. Similarly, reg 1 will be 25 to 21, you see, reg 1 will be IR 25 to 21, reg 2 will be 20 to 16, reg 3 15 to 11, offset 10 to 0. So, in this way I can use this cross sections in an assignment statement, even I can use them in an expression, like let us say I can write an expression like this also, like say I can write sum equal to, let us say IR 25 to 21 plus IR 20 to 16. So, I can write like this also. So, here what I am meaning is that 25 to 21 means this number, 20 to 16 means this number. I am adding these two 5-bit numbers and I am storing the result in another variable sum. Such things I can also do, right. So, I can take out a cross section from a given vector and I can do any kind of manipulations on it. Okay. Now, talking about multidimensional arrays and memories, now we can declare multidimensional arrays in Verilog, means of any dimension. Let us take two examples. Here reg 31 to 0, register bank again 15 to 0. What does this mean? First is reg 31 to 0. This is the declaration of a register of width 32 bit register. Now, we are saying that I have a register bank where there are 16 elements. So, we are actually talking about 16 32 bit registers, right. So, and when we access these elements, we will be accessing them using the 2 index values. Like here, if I just write, let us say register bank, if I just write 5, register bank 5, this will mean a 32 bit value, the content of the register number 5, because here I have declared register bank as an array of size 16, 0 to 15. So, when I say register bank 5, so it is one of those elements and each of these elements is of type reg 310, that means a 32 bit number. But here for integer, for example, integer is already a 32 bit by default. So, I need not have to specify this. So, I write matrix 7 0 15 0, this is a 2 dimensional matrix with 8 rows and 16 columns. Now, we will see later that when we use let us say memories in a design. So, one way, there are other ways also which let us see. So, one way is to declare a memory as a 2 dimensional array, multi-dimensional array. So, some examples of memory declaration is this. So, you can simply write reg some name membit 0 to 2047. This is a 2 kilobit memory. Total number of location is 2048 and each location contains 1 bit. But if you declare it like this, similar to this register bank, so there are 0 to 1023 1 kilo words, each word is of size 16. So, you can declare a memory like this. So, specifying constant values, you can specify constant values like this in either sized or unsized form. The syntax is you specify a size, then a single quote followed by a base, then a number. Here I have shown some examples. So, the base I have shown as binary or hexadecimal H. 4B0101 means a 4 bit binary number 0101. 1B0 means logic 0 1 bit. 12 hexadecimal means a 12 bit hexadecimal number 12 bit. B3C. So, this is B3C. Well, out of this I can have some x also, do not care also 8xf. This is 8, x means all xxxx f, and if I write only 25, this is a signed number and by default it will be put in 32 bits. So, whenever you are using integer or real numbers, you typically do not use the size specifier, they are typically expressed in unsized form, right. Okay. Now, talking about parameters, we shall be seeing parameters again later. So, parameter is something similar to a hash defined that you use in a C program. It is like a constant. We define a constant with a given name, and in the program whenever we use that name, we replace that name by that constant. So, this parameter is something like that. But when you declare parameter, we do not specify the size. The size automatically get deduced by the constant values that we are defining. Like we have given some examples, it will be clear. In the first example, I am saying parameter high equal to 25, low equal to 5. So, in the program, whenever there is an hi, this hi will be replaced by 25, and whenever there is lo, lo will be replaced by 5. Similarly, next example, up, down, steady. So, I am declaring 2-bit number, 00 means up, 01 is down, 10 is steady. So, if you use parameter in a program, it will make your program more readable. So, instead of writing 00 and 01, if you write up and down, it will be easier to understand, right. So, that is the main purpose of using this kind of constructs, parameter. Similarly, for a traffic light controller system, let us say you can define red as a 3-bit number 100, yellow as 010, green as 001. Okay. These are some examples. And just one Verilog complete module I am showing that uses a parameter. This is an n-bit counter. So, I am declaring it as an n. Okay. Clear, clock, count, clear and clock are the inputs, count is the output. This is 0 to n, and because I am using it on the left hand side, I am also declaring it as reg. So, this counter counts at the negative edge of the clock. So, it is neg edge. So, very similar to the previous one, if clear, count, you see here we have used the other kind of assignment less than equal to. So, the difference we will explain later. Okay. 0 else count equal to count plus 1. So, here if you just change this one line in the program, your module can change from a from a 7-bit counter to something, not 7, 8-bit counter, n plus 1 bit, 0 to n. Parameter n equal to 7 means it is a 8-bit counter. So, if I make it 15, it will become a 16-bit counter. Okay. So, you change just one line. Okay. That is the advantage of using parameters. So, with this we come to the end of this lecture. Again we shall be looking at some more features of the Verilog language in our next lectures. Thank you.